Welcome to the deep dive. Today we're tackling a really interesting challenge. What do you do when a database table just gets too big?
Yeah, we've got a great case study here. It's about how the team at AHA dealt with a massive audits table in their PostgreSQL database.
It really shows how even well-designed systems can hit scaling walls and, the clever fixes engineers come up with.
Exactly. We're diving into their journey with this table, which their Rails app used to track changes. Billions of rows.
Billions. Okay. So your mission today, as you listen, is to get your head around why these huge tables are a problem, what partitioning is, and like the actual steps and trade-offs involved in implementing it.
Right. It's super valuable stuff. Whether you're deep in tech or just curious about how software scales, you'll get insights into database architecture, performance tuning.
For sure. And our source is a really detailed article from the AHA Develop blog written by Mayvi Revels.
She lays out their whole process dealing with this giant audits table, exploring tools like PG Slice and PG Partman, and finally, their multi-stage approach using Postgres' own partitioning features.
Both inheritance and declarative partitioning.
Yeah, both within a Rails setup. It's quite a journey.
Okay, so let's set the scene. A decade of history. An audits table tracking everything.
Which led to billions of rows.
Yeah.
Billions.
Wow, and that means terabytes of storage. That's not just like a number, right?
Yeah.
That causes real problems.
Oh, absolutely. The article highlights some serious pain points. First, cost. We're talking huge Amazon RDS bills, like 5 figures a month, just for storage and backups.
Ouch. And backups themselves become risky.
Yeah, disaster recovery gets way more complicated. If the normal RDS snapshots failed, a full restore could take hours. That's a big operational risk.
And day-to-day performance must have suffered too.
Definitely. Query performance degraded significantly. The indexes, which are supposed to make searches fast, got so big they wouldn't fit in memory.
So lots of slow disk reads then.
Exactly. And even indexed lookups had to sift through way more data, full table scans. Basically impossible. Took forever.
But they found a pattern in how they use the data, right? This hot to cold thing.
Yeah, that was key. They realized over 90% of their queries hit only the last 30 days of data. Recent stuff.
Okay.
Older data was accessed much, much less frequently.
Like looking at recent bank statements versus ones from 10 years ago.
Precisely. So their first step was smart. They built an audits archiver.
What did that do?
It moved audits older than 12 months off to Amazon S3. Cheaper storage, practically unlimited.
And they checked it was all copied okay first.
Yep, very careful validation step before deleting anything from the main database.
Okay, so the really old stuff is safe in S3. But they still had billions of archive rows left in the main Postgres table.
Right, and just deleting those rows month after month wasn't a great solution either.
Why not? What's the problem with big deletes?
Well, it gets into how Postgres works internally with something called MVCC, multi-version concurrency control. Yeah. Rows aren't really gone immediately.
Exactly. They get marked as dead, but they stick around, creating overhead for queries until a process called VCU cleans them up. Massive deletes mean tons of these dead rows.
Slowing things down.
Yep. And big deletes also cause contention, fighting over resources, especially on the indexes.
Locks.
Yeah, index locking was a bottleneck, even if the old data itself wasn't changing. Plus, all those deletes can lead to table bloat, wasted space on disk.
Okay, so deleting wasn't the long-term answer. What was?
Declarative partitioning. That was their ultimate goal.
Right. Explain that again in simple terms, the filing cabinet analogy.
Yeah, exactly. You take your one giant overflowing table and you split it logically into smaller, manageable physical tables or partitions.
But the application still sees it as one table.
Correct. From the Rails app's point of view, it's just audits. But underneath, Postgres knows it's divided up maybe by month or some other range. Each partition has its own data, its own indexes.
And the article mentioned different ways to split it. Range, list, hash. Range partitioning is great for ordered data, like dates or IDs. You define ranges like IDs 1 to 1 million go here, 1 million to 2 million go there.
Okay.
List partitioning is for specific values, like maybe partitioning by country code or status, US rows here, UK rows here.
Got it. And hash.
Hash just spreads data evenly when there's no obvious order. Postgres uses a formula to assign rows.
And for their audits table with those time-based IDs, range partitioning makes sense.
Absolutely. It was the natural fit.
So what are the big wins you get from partitioning like this?
Several big ones. First, faster queries due to partition pruning.
Pruning.
Yeah, if your query filters on the partition key, like asking for audits from last month, Postgres is smart enough to only look in the partition that contain that data. It skips or prunes the rest.
Ah, so it doesn't waste time searching irrelevant data.
Exactly. Big speed up, especially for those common queries hitting recent data. And it keeps the relevant index parts hot in memory.
Nice. What else?
Detaching partitions is super fast. Remember the pain of deleting billions of rows? With partitioning, removing old data is often as simple as detaching the whole partition for, say, January 2023. It's a near-instant metadata change.
Wow, so you just disconnect that old partition.
Yep. Then you can archive it, drop it, whatever. Much cleaner than massive deletes.
Solves that whole MVCC and bloat problem from deletes.
Right. That's the third benefit: reduced overhead. No more massive delete operations causing bloat. Less VHU work. Less index maintenance strain. It's much more efficient for tables with that kind of life cycle.
Okay, partitioning sounds amazing,
Yeah.
but how do you actually partition a table that already has billions of rows? Sounds tricky.
It is very tricky. Moving rows. Too slow. Same problems as deleting. Copying rows needs way too much temporary disk space.
So they needed that no-move solution. How did that work?
The idea is to use an existing table as a partition. You create the new partition table structure, but then you tell Postgres, hey, treat this original giant table as the first partition. Then you do some clever renaming behind the scenes so the application starts talking to the new partition structure without noticing. Zero downtime, theoretically.
Theoretically. What's the catch?
The catch is validation. Before Postgres attaches an existing table as a partition, it has to check that every single row in that table actually belongs there, that it fits the partition's defined range.
And how does it check?
Full table scan.
Oh boy. On billions of rows?
Yeah.
That sounds long.
Very long hours, potentially. And worse, during that scan, it takes out an access exclusive lock.
Which means?
Everything stops,
Yeah.
no reads, no writes to that table, complete outage for the duration of the scan.
Yikes. Okay, that's a non-starter for a live system, so how did they get around that?
This is where the chick constraint trick comes in. It's pretty clever.
Go on.
So a chick constraint enforces a rule like all IDs in this table must be between X and Y. Postgres trusts valid chick constraints. If a constraint matching the partition range exists and is valid, Postgres can skip the full table scan during the attach.
Ah, okay. So they just add the right check constraint first.
Well, not quite. Creating a valid constraint also usually requires a full table scan and that same access exclusive lock to verify all the existing data.
Oh, back to square one?
Oh, most. But here's the magic. You can create the constraint as not valid.
Not valid.
Yeah, it means the constraint starts applying immediately to all new or updated rows, but Postgres doesn't check the existing data right away. Creating it like this is super fast and doesn't need the exclusive lock.
Okay, so you have this constraint that's not yet fully checked. Then what?
Then later, as a separate step, you run alter table validate constraint. This command does do the full table scan to check all the old data.
Yep.
But, and this is crucial, the validation uses a much friendlier lock. Share update exclusive.
Which allows?
It allows reads and writes to continue happening concurrently while the validation scan runs in the background.
Ah, so the scan still takes hours, but the application keeps working.
Exactly. It's disruptive in terms of database load, but not an outage. Once validated, the constraint is trusted, and then you can attach the table as a partition instantly without the scan or the bad lock.
That's a really neat sequence. Break down the locking operation.
Yeah, create not valid, fast, no lock, then validate constraint, slow scan, but allows concurrent access, then attach partition, instant, uses validated constraint.
Brilliant. But there was another snag, right? Data outside the planned ranges?
Yep. Just when they thought they had it figured out, they found historical data with weird attributed values way outside their expected ranges. Leftovers from old bugs, apparently.
Ghosts of IDs passed. So what did they do with those? They couldn't just throw them away.
No, the data was needed. This is where the default partition came in handy.
A catch-all.
Exactly.
Yeah.
Postgres lets you define a default partition for anything that doesn't match the other ranges. But they needed a way to get those outlier rows into the default partition before validating the constraints on the main data.
And how do they manage that without downtime?
They temporarily used an older Postgres feature, table inheritance.
Inheritance. How's that different from the declarative partitioning they were aiming for?
Inheritance is looser. Child tables inherit the parent's structure, and queries on the parent include the children. But Postgres doesn't automatically enforce partitioning rules or do partition pruning.
So it's more like just grouping tables.
Kind of. Crucially for them, attaching tables as children using inheritance doesn't trigger that full table scan and lock.
Ah. And how do they control where new data went in this inheritance setup?
With a before insert trigger on the parent table, this little piece of code would look at the id of every new row and manually route it to the correct child partition, the main one or the default one.
Okay, so inheritance was a bridge, a temporary fix to handle the outliers.
Precisely. It let them set up the structure, including the default partition, without the locking issues of immediately going declarative, and the trigger handled routing.
But it had downsides, right? Why only temporary?
A few reasons. One, maintaining that trigger logic is manual work. Add a partition, update the trigger. Two, no automatic partition pruning, so queries weren't as fast as they could be. It scanned all children.
And performance issues.
Yeah, with lots of partitions, query planning could slow down, and the trigger itself could become a bottleneck for high-volume inserts. So, good stepping stone, but not the final destination.
Got it. Okay, so let's walk through their actual rollout plan. It was multi-phased. Phase 0.
Phase 0 was prep work in their Rails app. Rails 7.1 didn't have great native partitioning support back then.
So they used a gem.
Yep, PG Party, and wrote some custom helpers too. Even with Rails 8 starting to add support, they found these tools useful.
What kind of helpers?
Things from managing migrations, querying partition boundaries, detaching inherited tables, managing stats, ensuring row-level security policies were consistent across partitions. They integrated it nicely.
Making it easier to manage from Rails. Okay, Phase 1, setting up inheritance.
Right. This is where they created the new parent table, partitioned audits, the default partition child table, and the first real monthly child partition.
With the check constraint for its ID range.
Yep. And they implemented that before insert trigger on the parent to route new data.
And the clever rename trick.
Exactly. They renamed the original audits table to something like audits P0, making it the first historical partition, then renamed the new parent partitioned audits to audits.
So the app just kept writing to audits, but now it was hitting the inheritance structure? Seamless.
Very smooth, zero downtime for that switch.
Okay, Phase 2, validating boundaries. This is about dealing with that historical data and the not valid constraints.
Correct. Now that inheritance was live, they added not valid check constraints to that historical audits P0 partition and any others they had.
Defining the expected ID ranges without locking.
Right. Then they had to find and move any rows with those weird out-of-range IDs from audits P0 into the default partition.
And then validate the constraints.
Then validate. That's the slow part, the background scan, using the share update exclusive lock, allowing the app to keep running.
And they cleaned up the default partition data.
Yeah. Investigated those rows, fixed IDs if possible, moved valid data back, and they set up CloudWatch monitoring on the default partition just in case new weird data appeared. Very thorough.
Okay, data integrity checked, constraints validated, ready for the final leap. Phase 3, declarative partitioning.
Yes. The grand finale.
Right.
With the check constraints validated, they could finally switch to the real deal.
How does migration work? Also zero downtime.
That was the goal. They created another new audits table, but this time using partition by range.
Yeah.
Checks and fully declarative. Same columns, indexes, constraints, security policies.
Okay.
Then, in one atomic transaction, detach all the child tables from the old inheritance parent, alter table, no inherit. Immediately attach those same tables to the new declarative parent using the validated check constraint ranges.
And because the constraints were validated, this attach was instant.
Instant metadata operation. No scan needed. Then, the final rename. Rename the old inheritance parent to old audits. Rename the new declarative parent to audits.
Boom. Application now using full declarative partitioning.
Without missing a beat. Then they could safely drop the old inheritance parent table and remove that before insert trigger. Routing is now handled automatically and efficiently by Postgres.
That is a seriously well-orchestrated migration. You mentioned indexes and constraints being critical for the attach step.
Absolutely vital for avoiding those exclusive locks during the switch to declarative. You need to pre-create matching indexes on the child tables before attaching them.
Using create index concurrently.
Yes, concurrently is key so you don't block writes while building the index. If the index exists when you attach, Postgres just links it up. No blocking.
And same for other constraints,
Like
not NL or foreign keys.
Yes, ensure all necessary constraints, not all, check, foreign keys, exist on the child table before attaching. Otherwise, Postgres might try to add and validate them during the attach, causing locks. Primary key and unique constraints rely on their underlying indexes being present.
So preparation of those child tables is everything.
It really is. Get the children ready with identical structures, indexes, and constraints. Validate the check constraints, then perform the atomic detach attack rename.
Okay, so now they have this shiny declarative partition table. How do they manage it going forward? Creating new partitions, removing old ones?
They automated it using Rails scheduled jobs. They built a reusable partitionable biad concern for their Rails models.
A concern, like a reusable module.
Yeah, it bundled logic for things like creating the next month's partition ahead of time.
Proactive.
And detaching the oldest partition once its data was safely archived to S3, and eventually dropping those detached partitions to reclaim space.
Did it help with querying too?
Yes, it included a scope, increated to trange, which translated a timestamp filter into the appropriate id range filter, helping Postgres use partition pruning effectively.
So automation handles the day-to-day creation and cleanup. Smart.
Essential for long-term maintenance.
One last point. Why didn't they just use pgpartment, the popular extension for this?
Good question. They considered it, but pgpartment depends on another extension, pgjobmon, for monitoring and scheduling.
And that wasn't available on RDS.
Right, not easily on Amazon RDS where they host their database. They also preferred tighter integration with their existing tools, Sentry, Datadog, CloudWatch, for observability.
More control, better visibility within their stack.
Exactly. But they smartly use pgpartment's naming conventions, keeping the door open to potentially switching later if needed.
Makes sense. Okay, let's wrap this up. What are the main takeaways from this whole journey?
I think first, really understand your data access patterns. That hot to cold discovery was critical for AHA. Second, partitioning is powerful but complex. Third, migrating a live large table requires meticulous planning, that multi-stage approach. Handling locks using tricks like not valid constraints, it's all key for zero downtime.
And automation for maintenance is non-negotiable.
Absolutely. You can't manage partitions manually long term.
So for you listening, this has hopefully been a really concrete look at tackling a major scaling challenge. You see the database optimization techniques, the trade-offs, the careful engineering needed.
And it leaves us with a thought, maybe. This idea of partitioning, breaking a huge thing into smaller, manageable units. Where else could that apply? Think about software architecture, project management, maybe even just how you organize your own work or life. Are there big, complex things you can break down like this?
Definitely something to chew on. If you want all the nitty-gritty details, check out the original article, Partitioning a Large Table in PostgreSQL with Rails by Maeve Revels on the AHA Develop blog.
It's a great read.
Thanks for joining us on this deep dive. We'll catch you next time.